Hello everyone, welcome back to my channel InfoSec Lab. We are going to continue our series from TryHackMe's web app pen testing, and today's topic is going to be race conditions. Race condition is a very common vulnerability in web applications. We're going to go over what it is, how to detect, how to exploit this vulnerability, and last but not least, we're going to learn some mitigation strategies, how to prevent such vulnerabilities in web applications. Now, without further ado, let's get started. Introduction. Let's say that we're tasked with testing the security of an online shopping web application. Many questions popped up. Can we reduce a single $10 gift card to pay for a $100 item? Can we apply the same discount to our shopping cart multiple times? The answer is maybe. If the system is susceptible to a race condition vulnerability, we can do all of this and more. In this room introduces the race conditions vulnerability. A race condition is a situation in the computer programs where the timing of events influences the behavior and the outcome of the program. It typically happens when a variable gets accessed and modified by the multiple threads. Due to a lack of proper lock mechanisms and synchronizations between the different threads, an attacker might abuse the system and apply discount multiple times or make money transactions beyond their balance. The learning objectives of this room is to know what a race condition vulnerability is, using Burp Suite repeater to explore a race conditions vulnerability. Along the way, you also learn about the thread and multi-threading and some state diagrams. As usual, this room also has some prerequisites, which is how the web works, the packets and frames, and then, of course, the Burp Suite basics. Alright, so what's multi-threading? In this task, we provide a quick overview of the following terms: programs, process, thread, and multi-threading. Programs. A program is a set of instructions to achieve a specific task. You need to execute the program to accomplish what you want. Unless you execute it, it won't do anything and remains a set of static instructions. Think of it as a recipe. If you downloaded a new coffee recipe that includes a variety of herbs such as cardamom and cinnamon, these are instructions. Unless someone carries out the above instructions, no coffee will be served. Compare this to a mini Flask Python Hello World server. The code below dictates that the app will listen on a port 8080 and respond with a minimal greeting HTML page that contains Hello World. However, we must run these instructions, which is the program, before we expect to get any greeting pages. Please note that the Flask code below is shown in demonstrated purpose only. We didn't provide an environment to run it as it is outside the scope of this room. Okay. Processes. One afternoon, you decide to try out a new coffee recipe you downloaded online. You start going through the recipe one step at a time. You are in the process of making this coffee recipe. While in the process of executing the instructions, you might get interrupted by an urgent call. Or you might work on another job while waiting for the water to heat. Interruptions and waitings are generally unavoidable. The act of carrying out the recipe instructions to make coffee is similar to the process of executing program instructions. A process is a program in execution. In some literature, you might come across the term job. Both terms refer to the same thing, although the term process has superseded the term job. Unlike a program, which is static, a process is a dynamic entity. It holds several key aspects. In particular, program, the executable code related to the process, memory, temporary data storage, state. A process usually hops between different states. After it is in a new state, i.e. just created, it moves to the ready state, i.e. ready to run. Once the CPU allocates time for it, it goes to the running state. Furthermore, it can be waiting state, pending I/O, or event completion. Once it exits, it moves to the terminated state. And this is a diagram describing the state of a process. If you run the Flask code above, a process will be created and it will listen to incoming connection at port 8080. In other words, it will spend most of its time in the waiting state. When it receives an HTTP GET request, it will switch to the ready state, waiting for its turn to run based on the CPU scheduling. Once in the running state, it sends the HTML page to the client and returns to the waiting state. From the server's perspective, the app services the client sequentially. The client requests are processed one at a time. Now, please note that the Flask command shows below is for demonstrative purposes only. Threads. Let's wrap up with another coffee analogy. Consider the case of a commercial espresso machine in a coffee shop. Let's say that it has two portafilters. At the start of a workday, the barista turns the espresso machine, and whenever a customer orders an espresso, one portafilter is used to prepare a special shot for them. Does another customer order an espresso? No problem. The second portafilter will to the rescue. The warmed-up espresso machine is in the process. Each new order is assigned a portafilter. That's the analogy of the thread. A thread is a lightweight unit of execution. It shares various memory parts and instructions with the process. In many cases, we need to replicate the same process repeatedly. Think of a web server serving thousands of users at the same page. We can adopt one of two main approaches. 0. One process is running. It serves one user after the other sequentially. New users are in queue. Parallel. One process is running. It creates a thread to serve every new user. New user only in queue after a maximum number of running threads is reached. The previous app can run 4 threads using Unicorn. Unicorn, which is also called the Green Unicorn, is Python WSGI HTTP server. WSGI stands for Web Server Gateway Interface, which bridges the web servers and Python web applications. In particular, Unicorn can spawn multiple worker processes to handle incoming requests simultaneously. By running Unicorn with the workers equals 4 option, we are specifying that we want 4 workers ready to tackle client's request. Moreover, threads equal 2 indicates that each worker process can spawn 2 threads. Now, again, the below code is also for demonstration purpose only. We don't have to do any of this. It is worth noting the following. It is impossible to run more than one copy of this process as it binds itself to the TCP port 8080. A TCP or UDP port can only be tied to one process. Process can be configured with any number of threads, and HTTP requests arriving at port 8080 will be sent to different threads. You downloaded an instruction booklet on how to make an origami crane. What would the instruction booklet resemble in computer term? Program. Let's program. What is the name of the state where the process is waiting for I/O event, meaning the input/output? Should be waiting. Real-world analogy. Picture the following situation. You call a restaurant to reserve a table for a crucial business lunch. You're familiar with the restaurant and its setup. One particular table, number 17, is the preferred choice, considering it has a nice view and is relatively isolated. You call to make a reservation for table 17. The host confirms it is free as no reserve tag is placed on it. At the same time, another customer is talking with another host and making a reservation for the same table. Who really reserved the table? That's a race condition. Why did this happen? This unlucky situation happened because more than one host was taking reservations. Furthermore, it took the host a few minutes to fetch the reserve tag and put it on the table after updating the daily reservation book. There is at least a 1-minute window for another client to reserve a reserved table. Similarly, when one thread checks a value to perform an action, another thread may change that value before the action takes place. Let's take a look at these 2 examples. Example A, let's consider that we have a bank account with $100. There are 2 threads trying to withdraw the money at the same time. Thread number 1 checks the balance. It sees $100. It withdraws $45. Before thread 1 updates the balance, which is $55 remaining. Thread number 2 also checks the balance and it sees $100. Now, of course, this is incorrect and withdraws $35. We cannot 100% sure which thread will get to update the remaining balance first. However, in this scenario, let's assume that it's thread number 1. Thread number 1 will set the remaining balance to $55. Afterwards, thread number 2 might set the remaining balance to $65 if not appropriately handled. Thread number 2 calculated $65 should remain in the account after the withdrawal because the balance was $100 when thread number 2 checked it. In other words, the user made 2 withdrawals, but the account balance was deducted only once for the second because thread number 2 says so. Example number 2. We have a bank account with $75. There are also 2 threads trying to withdraw the money at the same time. Thread number 1 checks the balance and sees $75 and withdraws $50. Before thread number 1 updates the balance, thread number 2 checks the balance and also sees $75, which is incorrect at this point, and withdraws $50. Thread 2 will proceed with the withdrawal, although such a transaction should have been declined. Examples A and B demonstrate a temp object to temp of use vulnerability. Example code. Consider the following Python code with 2 threads, simulating a task completion by 10% increments. These 2 parts start together. They do nothing except print about use on the screen. Consequently, one would expect them to finish simultaneously, or at least the result should be consistent. However, in the program above, there is no guarantee which thread will finish first and how early it will be. Below is the first execution output. Okay. Below is second execution output. Running this program multiple times will lead to different results. In the first attempt, thread number 2 reached 100 first. However, in the second attempt, thread number 2 reached 100 second. We have no control over the output. If the security of application relies on one thread finishing before the other, then we need to set mechanisms in place to ensure proper protection. Consider the following 2 examples to better understand the bug's gravity when we leave things to change. Okay, on a text box, you can save a Python code and run it multiple times to observe the outcome. For example, if you save it as raise.py, you can run a script using the follow command python raise.py. Alright, it's pretty straightforward. You can just copy this code, put it in terminal, try running that, and see different results. Causes. As we saw in the last program, 2 threads were changing the same variable. Whenever the thread was given CPU temp, it rushed to increase by x by 1. Consequently, these 2 threads were racing to increment the same variable. This program shows a straightforward example happening in single host. Generally speaking, a common cause of race condition lies in the shared resources. For example, when multiple threads concurrently access and modify the same shared data. Examples of the shared data are database record and an in-memory data structure. There are many sort of causes, but we'll mention 3 common ones. Parallel execution. Web servers might execute multiple requests in parallel to handle concurrent user interactions. If these requests access and modify shared resources or application states without proper synchronization, it can lead to race conditions and unexpected behavior. Database operations. Concurrent database operations, such as read, modify, write sequences, can introduce race conditions. For example, 2 users attempting to update the same record simultaneously may result in inconsistent data or conflicts. The solution lies in enforcing proper locking mechanisms and transactions isolation. Third-party libraries and services. Nowadays, web applications often integrate with third-party libraries, APIs, and other services. If these external components are not designed to handle concurrent access properly, race conditions can occur when multiple requests or operations interact with them simultaneously. Answer the questions. Does the presented Python script guarantee which thread will reach 100% first? No, it does not. In the second execution of Python script, what is the name of the thread that reached 100 first? Thread 1, as it's been explained above. Web application architecture. Client-server model. The web application follows the client-server model. Client is the program or application that initiates the request for the service. For example, when we browse a web page, our web browser requests a web page or file from the web server. Server is a program or system that provides these services in response to incoming requests. For instance, the web server responds to an incoming HTTP GET request and sends an HTML file to requesting web browser. Generally speaking, the client-server model runs over the network. The client sends its request over the network, and the server receives it and processes it before sending back the required resources. Typical application. A web application follows a multi-tier architecture. Such architecture separates the application logic into different layers and tiers. The most common design uses 3 tiers. Presentation tier. In web applications, this tier consists of the web browsers on the client side. The web browser renders the HTML, CSS, and JavaScript code. Application tier. This tier contains the web application's business logic and functionality. It receives client's requests, processes them, and interacts with the data tier. It is implemented using server-side programming languages such as Node.js and PHP, among many others. Data tier. This tier is responsible for storing and manipulating the application data. Typical database operations include creating, updating, deleting, and searching existing records. It is usually achieved using a database management system. Example of DBMS include MySQL or PostgreSQL. States. Let's visit some examples from the business logic before diving deeper. We'll consider the following two examples: validating and conducting money transfer. Consider the example of transferring money to a friend or your other account. The program will progress as follows. The user clicks on the Confirm Transfer button. The application queries the database to confirm that the account balance can cover the transfer amount. The database responds to the query. If the amount is within the account limits, the application conducts the transaction. If the amount is beyond the account limits, the application shows an error message. Alright, pretty straightforward. If your account has $100 and if you request $150, obviously it's going to show you an error message that you don't have enough money or insufficient fund. In an ideal scenario, the code above leads to two program states: amount not sent and amount sent. Amount not sent right here, amount within the limit, then amount sent. If amount exceeds the limit, amount not sent. Okay. So basically there are two, in this scenario, there are two actions, either sent or not sent. Validating coupon codes and applying discount. The user goes to their shopping cart and adds a coupon to get a discount. The steps might be something follow. The user enters a coupon. The application queries the database to determine whether the coupon code is valid and whether any constraint exists. The database responds with validity and constraints. The discount is applied if the code is valid and there's no constraints on applying it for this user. An error message is displayed if the code is invalid or there are constraints on applying it for this user. Apply coupon application. Send queries to the database that respond to the query. Is it valid? Yes, apply discount. Nope, display error message. Straightforward. So in this scenario or in this example, we have two states: coupon applied and coupon not applied. Let's continue our analysis of applying discount coupon. Ideally, we expect two states: coupon not applied and coupon applied. However, this is too much simplistic to depict a real sophisticated scenario. We can add an intermediate state, checking coupon applicability. Depending on how the application is developed, we can expect more states. However, checking coupon applicability might involve two states: checking coupon validity and checking coupon constraints. A coupon might be valid, but existing constraints prevent it from being applied. Similarly, coupon applied might be divided into two states, one of which is recalculated total. So coupon applied. So we add coupon to check coupon validity. If coupon is not valid, then coupon is not applied. If coupon is valid, we check for the constraints right here. If there's no constraint, coupon applicable. And then once coupon is applied, we have to recalculate the total. Once the total is recalculated, it will mark coupon as applied and then it shows right here. It goes to the coupon applied state. If there are some constraints that prevent this coupon from being applied, then the coupon will not be applied. So it will go back to the states right here. So this is going to be the intermediate state. Why is this important for race condition? In the above state diagram, we can see that we pass through multiple states before the coupon is marked as applied. Let's draw the states on a time basis, and it shows below. Coupon not applied, add coupon, check coupon validity, check coupon constraints, recalculate the total, mark coupon as applied, and then coupon applied. This is supposed to be an order in which each of these events should happen. There's a time window between the instant we try to add a coupon and the instant where the coupon is marked as applied and cannot be applied again. As long as the coupon is not marked as applied, most likely no controls prevent it from being accepted repeatedly. We might be able to apply it multiple times during this time window. This situation is similar to when considering the state for a program making a money transfer. Although ideally speaking, it would be two states. Considering the business logic, we can easily update the diagram to include three states. The reason is that we expect some time spent checking the account balance and limits. Although this amount of time might be brief, it is not zero. If we dig deeper, we can uncover more hidden states. So check the balance and account limits. If the amount within the limits, amount sent. If the amount exceeds the limits, amount not sent. So this is what happens when we press the button confirm transfer. However, even if the web application is vulnerable, we still have one challenge to overcome: timing. Even if the vulnerable applications, this window of opportunity is relatively short. Therefore, exploiting it necessitates our request. Even in vulnerable applications, this window of opportunity is relatively short. Therefore, exploiting it necessitates that our requests reach the server simultaneously. In practice, we aim to get our repeated requests to reach the server only milliseconds apart. So how can we get our duplicate requests to reach the server within a short period of time? We're going to use Burp Suite. So how many states did the original state diagram validating there to? How many states did the updated state diagram validating conduct money? We have 3. Remember, the original state was amount sent and an amount not sent. So an updated one is that amount sent, amount not sent, and checking the balance. How many states did the final state diagram of validated coupons and applying discount? Let's go back, take a look at it. At coupon 1, check coupon validity. 2, check coupon constraint. 3, recalculate total. 4, 5. We have 5. Exploiting race conditions. First, we're going to have to start a machine. Here, we're going to take a look at an application that belongs to a mobile operator, and it allows phone traded transfer. In this demo, we will check if the system is susceptible to a race condition and try to exploit it by transferring more credit than we have in the account. We're going to open the browser and go to the URL right here. It's 10.201.17.7. First, we need to explore and study how the target web application receives HTTP requests and how it responds to them. Use the Burp Suite proxy. Click Open Browser under the Intercept tab. If you get an error message about enabling proxy browser sandbox, you must manually change the settings. In this case, click Settings on the top right of the Burp Suite window. Click on the Burp browser under the Tools and check Allow Burp browser to run without a sandbox. Using the bundle browser, we can browse the target sites and study how it processes our HTTP request, notably the post HTTP requests and related responses. The HTTP History tab logs every HTTP request and the respective response. Log into either of the accounts and click the Pay and Recharge button. Let's make a credit transfer. Click on the Transfer button and enter the mobile number of the other account along with the amount that you want to transfer. You can try to transfer an amount that exceeds your current balance and a small amount, such as $1, to see how the system responds. So let's log in with the first user, and the password is pass1234. We also have to open Burp Suite. But basically, this is what it looks like on the front end. We want to transfer money to the other account, and amount is 0. Let's say I want to transfer 1 cent. Sorry. And then click transfer. We see a message right here, transaction successful. And when we take a look at the dashboard again, we see that the balance, our current balance is $5, which is a regular behavior, right? So let's try to transfer an amount that's more than $5, which is $7 transfer. We should get an error message, transaction decline, which is expected. So how does it look in the back end, behind the scene? Let's try again. Pay and recharge. This time we try $7 again. Burp. We open here and then we make sure that Burp has already intercepted the traffic. Now we can click transfer button. We see the traffic right here. Let me try to make it bigger. Where was the displays? Right here. I'm going to make it size 14. Okay, that's good enough. And another thing is like HTTP. I think it was interface. I want to make it bigger, 15, font size 15. So we can easily see the tab right here. Send it to repeater. Okay, so this is what happened behind the scenes. It sends a post request to this following URL, and this is the post data, the target phone number, the confirmation target phone number, and the amount that you want to transfer. What's gonna happen when you click send? You're gonna get a decline, right? Dashboard transaction decline with a message insufficient balance. Okay, which is something we expected. So now what's gonna happen if we try to send an amount that's reasonable? Click transfer. Over here, we press Ctrl R, which will send a request to the repeater. Over here, we see the amount is $1, so we should see a successful message. Click send. And transaction is successful. We go back over here, turn off the interception. The current balance is only $4, meaning that we have successfully transferred $1 to the other account. Now that we have seen how the system reacts to valid and invalid requests, let's see if we can exploit a race condition. Right-click on the post request we want to duplicate and choose Send to Repeater. Okay. And so we go to HTTP history, right-click data, which one that we want to use. Let's say we want to use this one, so right-click on this one, Send to Repeater. Over here, let's just clear these two. We want to create a group, so right-click on the tab, create a group. Now in this tab, we're going to duplicate the current repeater tab. So we're going to right-click this one, duplicate tab, and we're going to enter the amount of tabs that we want to duplicate. In this case, I'll do 20. As a result, in this group one, there are 21 tabs with the same thing. What I'm going to do next is click on the arrow right here and select Send Group in Parallel and Send. And eventually, if we take a look at these tabs right here, we can see that we have several tabs with a transaction successful. Now remember that the current balance is $4, right? The first 4 tabs should be successful. So 1, 2, 3, 4 should be successful. And the fifth tab it should display a decline message. But here you can see that the transaction is successful. The 6th one, 7th one, 8, 9, 10 similarly, meaning that the application is vulnerable to race condition. And because we send all the tabs at the same time in parallel, it causes the application to send more money than it has in the bank account. We can actually double check by checking the balance right here. We have negative $18. Let's log into the other account, which is this one. Password is pass 1, 2, 3, 4, and see we have $30. So basically, that's how we exploit the race condition. Let's do it again. From this account, I want to transfer money back to the other account right here. So what I'm gonna do is, let me close all the tabs right here. What I'm gonna do is to intercept the traffic one more time. Make sure the intercept is on. No, not right. Now, let's say I'm an attacker. I am greedy. I don't want $30. I want $100. So what I'm gonna do is try to exploit this race condition vulnerability in this application and try to get as much money as possible from this current balance. So what I'm gonna do is the same thing. Intercept the traffic when I transfer the money. But here, I send it to repeater and I add it to a new group. In this group, I'm going to duplicate the tabs for another 20 tabs. Each of them will transfer $30. Now I have 21 tabs and I'll click send group in parallels. I'll send it. And I should be having several tabs with successful message. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, time to check the other balance. Pass 1, 2, 3, 4. We got $612. That's a lot of money. And we also got a flag right here. Full race. Let's copy it. Now let's go over these options over here that we see and see what they do and why I chose send group in parallel instead of these other two options. Let's take a look. Sending request group in sequence. Sending the group in sequence provides two options. Send group in sequence in a single connection and send group in sequence in separate connections. Send group in sequence over a single connection. This option establishes a single connection to the server and sends all the traffic requests in the group tabs before closing the connection. This can be useful for testing potential client-side distinct vulnerabilities. So basically, it's not for race condition vulnerabilities. Send group in sequence over the separate connections. As the name suggests, this option establishes a TCP connection, sends a request from the group, and closes the TCP connection before repeating the process for the subsequent request. We tested this option to attack the web application. The screenshot below shows that 21 TCP connections for the different post requests in the group we sent. The first group, labeled 1, comprises 5 successful requests. We could confirm that they were successful by checking their respective responses. Furthermore, we noticed that each took around 3 seconds, and as indicated by the duration, labeled 3. It's right here. So these are the successful transactions, which took about 3 seconds. The second group, labeled as 2, shows 16 denied requests. The duration was around 4 milliseconds. It is interesting to check the relative start time as well. The screenshot below shows the whole TCP connection for a request. We can confirm that the post request was sent in a single package. Yeah. Second option, send requests to the group in parallel. Using the send the group's request in parallel would trigger the repeater to send all the requests in the group at once. In this case, we notice the following as shown in the screenshot below. In the relative start column, we notice that there are 21 packets were sent within 0.5 milliseconds. Label was right here. So basically, the tabs are almost identical. Only one request was successful. They resulted in a successful credit transfer. Each request took about 3.2 seconds to complete. Label 2 right here. By paying close attention to the screenshot above, we notice that each request led to 12 packets, which is right here, label number 3. However, in the previous attempt, sent in sequence, we see that each request required only 10 packets. Why did this happen? According to sending group HTTP request documentation, when sending in parallel, repeater implements different techniques to synchronize the request arrival at the target, i.e., they arrive within a short time per frame. The synchronization technique depends on the HTTP protocol being used. In case of HTTP 2 version 2 plus, the repeater tries to send the whole group in a single packet. In other words, a single TCP packet would carry multiple requests. In case of HTTP 1, the repeater resorts to the last byte synchronization. This trick is achieved by withholding the last byte from each request. Only once all the packets are sent without the last byte are the last byte of all requests are sent. The screenshot below shows how the post request sent over the two packets. So you need to get either the account to get more than $100, which we did, and the flag is TryHackMe phone raise. In short, after exploring these options, we know that in order to exploit the race condition vulnerabilities, most of the time we use the send group in parallels, meaning that in one single connection, at the same time, we send all the requests to the server. Detection and mitigation. Detecting race conditions from a business owner's perspective can be challenging. If a few users redeem the same gift card multiple times, it would most likely to go unnoticed unless the logs are actively checked for certain behaviors. Considering that race conditions can be used to exploit more subtle vulnerabilities, it is clear that we need the help of penetration testers and bug bounty hunters to try to discover such vulnerabilities and report their findings. Penetration tester must understand how the system behaves in the normal conditions and when enforced controls are enforced. The control can be use once, vote once, rate once, limit to balance, and limit to 1 every 5 minutes, among others. The next step would be try to circumvent this limit by exploiting race conditions. Figuring out different system states can help us make educated guesses about time windows where a race condition can be exploited. Tools such as Burp Suite repeater can be great at starting point. Mitigation. We will list a list of mitigation techniques. Synchronization mechanisms. Modern programming languages provide synchronization mechanisms like locks. Only one thread can acquire the lock at a time, preventing others from accessing the shared resources until it's released. Atomic operations refer to indivisible execution units, a set of instructions grouped together and executed without interruption. This approach guarantees that an operation can finish without being interrupted by another thread. Database transactions. Transactions group multiple database operations into one unit. Consequently, all operations within the transaction either succeed as a group or fail as a group. This approach ensures data consistencies and prevents race conditions from multiple processes modifying the database concurrently. Challenge web app. Following what you have learned, it is time to attempt discovering and exploit a race condition without guidance. So we're going to have this URL right here, and we're going to have 3 accounts. This web application belongs to a bank and allows clients to transfer online money. You need to get one of these accounts to amass more than $1,000. Okay, let's take a look at one of these accounts. 4621 Blue Apple. Not now. Let's take a look at the request, see how it is in the backend. So we're going to intercept this request, but before we do that, right here, let's transfer $10. Continue. This is going to be the request, and when we click send, we see something like this, true, meaning that the transaction was successful. You can actually double check by which one did we transfer to? Transfer to 6282. So we're going to log in 6282. We see that we have $109.5. Right, so that's how the request looks like, and let's see what an invalid request looks like. So we have 61 Blue Apple. Not now. We can actually we can actually try to intercept another traffic, but in this case, we can just reduce this one and try $100. Now, the fee is going to be 5. Let's see if it works. And the content is going to be $55. Let's try resending this. What do we get? We get the false. We don't get anything right here, so there's no indicators that it's a fail. So let's try intercept another traffic, which is this one. No, not this one. $100. Continue. Transaction fail. $100. And we're going to intercept that in the Burp Suite. Peter. What does it look like? Oh, same thing. So yeah, this is how it looks like in the back end. Now we're going to try to exploit the race condition vulnerability. We know from the previous example that we can try to group everything into one tab, and from there we can actually try to send all the requests at the same time. Let's try that again. So how much money do we have? We have $90. Let's try setting to this guy. $90. Subordinate staff. Okay, just set the traffic. Continue. Send it to repeater right here. And then try to add to a group tab. In this one, we try to duplicate for 20 times. And we're going to send group in parallel. The server encountered internal errors and wasn't able to complete your request. Oh, so I guess because there are so many requests at the same time, it causes the internal server. Oh, by the way, we have several tabs that results in true. So this is 1 successful transaction, 2 successful transactions, internal error, internal, 3 successful transaction, 4, 5, 6, 7, 8. Okay, so we have a couple of internal server errors and a couple of successful transactions. Let's double check. Drop everything. Disable. Let's log out and check this second account. White horse. White horse. Okay, we have $208, $80. Not very much, but we were able to confirm the vulnerability. Okay, so from here, let's try sending all the money to the last one, which is this guy. $280. The same concept. Intercept that using Burp Suite and send this one to repeater. From here, let's delete everything so it's easy for us to see. Delete this one. Oh no. Okay, there's something wrong. Continue. Right here. Send this one over here. We have a post request to this account number 9317. We're going to create a new group, and within this group we're going to duplicate the tabs 20 times, and we do the same thing, send group in parallel. Let's try that. Okay, so we've got several successful transactions, which is good. Let's see if we can achieve $1,000 or more in the other account. Over here we have 9317 and password is green orange. Yay, we got $1,962. And the flag is this one. That's it for the room. In this challenge, we were able to exploit a race condition vulnerability in a web application. If you have any questions or concerns about this room or any concepts, please reach out to me. And thank you very much for watching. I'll see you next time. Bye.